Hello, everyone. My name is George Silva, and I'm going to be talking about reinforcement learning today. Specifically, I'm going to be talking about reinforcement learning with deep Q networks. That's an exciting new action that we're making available in VIA. The first thing I'm going to do is introduce you to reinforcement learning. And you may have heard about names like AlphaZero, AlphaGo, and AlphaStar, and these are computer programs that have been beating the these are computer programs that have beaten human champions in board games, in games such as chess, Go, and even real-time strategy games. What do all of these things have in common? They use reinforcement learning. And that's what we're going to describe today. What is reinforcement learning? So reinforcement learning is the field that handles sequential decision making with minimal assumptions. It's a generalization of control theory. It is highly related with optimization, but has fewer assumptions. Namely, we may not have a fixed objective function, and we don't necessarily know the optimality gap or know when a solution is optimal. There are also differences between reinforcement learning and other types of machine learning, such as supervised machine learning that you may have heard about. And like supervised machine learning, you don't necessarily always take the best immediate action, the one that minimizes the immediate reward for that moment. You want to minimize the long-term reward, which means that sometimes, like in chess, you are willing to sacrifice a piece so that you move to a more advantageous strategic position. So it's all about long-term reward. And how does reinforcement learning relate to other types of machine learning? Well, in supervised learning, you typically know the labels. Either we are doing regression or classification, so you have features and you have labels and you know those values. Those are examples that we are using in supervised training. In unsupervised learning, you typically do not have labels, but you suspect that there are groups, or you might be trying to find an alternate representation of your data using dimensionality reduction. Reinforcement learning is different from either of these two types of machine learning. You don't have a label, and you are learning based on interactions, sequential interactions with an environment. So your goal in reinforcement learning is to train an agent, which is going to be a computer program that takes actions. Those actions affect an environment, which is either some business process or some piece of equipment in the real world, or it is a simulation. And you definitely want to use a simulation when you are training, initially when you're training the agent, when it doesn't know a good model yet. And so your agent that you train takes actions, and the environment needs to communicate back two important pieces of information. The immediate reward of your action, and you are going to be accumulating multiple immediate rewards, because again, you are interested in long term. And also the state. The state is going to be some numerical representation of how is your system right now? What is the position of your system? What is the state of your system? And those two pieces of information are going to be communicated back to the agent, and then the cycle repeats itself. You take the next action and receive the next immediate reward and the state. Not to go into a lot of mathematical detail, but the most important concepts in reinforcement learning are the state at time t, which we see here as S of t, action at time t, immediate reward at time t, R of t, as well as a value function and a policy. The value function v and the policy pi. And the value is the algorithm's best estimate of what is going to be on average the cumulative reward if you continue following a specific policy or model. And pi, the policy, is really the reinforcement learning equivalent of a predictive model. It is a mapping that, given certain action at a certain state, what is going to be either the probability distribution of actions, and that's for stochastic policies, or what should be the action taken at that time for deterministic policies. And this brings the case of stochastic policies. Why would you want to take actions at random according to a certain probability distribution? Well, think of this example. You are an Air Force pilot and you are involved in a dogfight. You definitely want to take random actions. Otherwise, people can predict your motions. So it really depends on what problem you have, whether you have a deterministic or a stochastic policy. And governing all of this, the main fundamental mathematical law that governs reinforcement learning is the Bellman equation. It simply states that the estimate of the value at a certain state at ST, if you follow policy pi, is recursively defined as, for each time step, when you take an action, according to policy pi and according to those probability distributions, how are you going to accumulate those rewards? And the most important number here is going to be this gamma, which simply is a discount value. It's like in finance. Future rewards count a little less than immediate rewards, but they do count and they do get accumulated. So this is the main relationship, the main recursion that is used in reinforcement learning. So this is all great. But you may have heard about deep reinforcement learning. How does reinforcement learning, which is a field that has existed for a few decades, how does it relate with deep learning and deep neural networks? It turns out that in order to estimate that value, and also in order to try to find those actions and those distributions over actions, you want a function estimator. And it turns out that deep neural networks are excellent function estimators. So you do use deep neural networks as function estimators or function approximators within reinforcement learning. That's how both fields are related. In the specific case of deep Q networks, which are a type of deep reinforcement learning, you are going to be using a deep neural network to map from the state S directly to the policy. So this will you will have a number of outputs in this deep neural network on the left that is equal to the number of possible actions that you can take, and the deep neural network will estimate the policy. And that means the agent, based on this deep neural network, will take a certain action. It will go to the environment, and the environment will respond by changing its state, giving you the next state and giving you an immediate reward. It's also important to note that you need to do this while you are training, but you don't need to transmit all the same information when you are deployed, when you have finished training a policy and you deploy. And the main difference is that you don't necessarily need to transmit the immediate reward when you are in deployment. You still need to transmit the state, and you still have the agent communicate the proposed action to the environment. But at this point, once the agent has been trained, you no longer need to have the immediate reward being transmitted back from the environment to the agent. And by the way, again, typically when you train, you use a simulated environment. And when you deploy, then you are free to use your agent in a real environment, in the real business process that you're trying to control. So this is great, but how can you do reinforcement learning in VIA? And let me start by introducing to you the reinforcement learn action set. This is an action set in VIA that has multiple actions within. It has training actions for two types of algorithms, a fitted queue network and a deep queue network. And it has a scoring action, RL score, as well as it includes support for A-store models, allowing you to use the RL export model action to create A-stores once you have trained a policy. So this makes it compatible with pipelines that you may have that already use data that is in VIA, as well as other predictive model A-stores. Additionally, remember, we need an environment, and this action set, the reinforcement learn action set, provides you with compatibility with well-known standards such as OpenAI Gym. So you can use existing environments that are available in OpenAI Gym, or you can develop your own, provided you respect the same API as OpenAI Gym. So this gives you a lot of flexibility. And I'll take this opportunity to describe very briefly a demo, and then I'll show you the code that you actually are going to use to run this demo. Let me introduce you one of the environments that's well known in the field. It's the lunar lander problem, and in this is sort of a little game where you try to land a small spacecraft on the surface of the moon, but you need to make a soft landing. You start always at the top of the screen, and you're trying to land between the two yellow flags, and the ideal landing position, the landing pad, is always at position 00 in this screen. Now, what is the representation of the state? It includes the coordinates at every time, the velocity and the angle of the spacecraft. And how is the reward computed? Well, if you land successfully, you get a reward that goes between 100 and 140. If you crash, and crashing is defined as you hit the ground with too high a velocity, then you take a negative reward, so a penalty of -100. And now depends also on the quality of your landing. If both your legs land at the same time on the ground, for each leg you get +10 reward. You also want to conserve fuel. So you want to be efficient in your fuel use, so you don't want to use your thruster too much. So whenever you fire your main engine, you take a penalty of 0.3 for every frame in this video. And what actions can the algorithm take? Really, there are only 4 possible actions: left thruster, right thruster, main thruster, and do nothing. So just let the vehicle coast, following its current velocity. All right, so now let's switch to the demo. I will show you a Jupyter notebook with Python code that gives you an example of how you can use reinforcement learning in VIA. And let's begin with this first part where you are going to use SWOT. So as always, when you're connecting to SAS and using Python, you import SWOT, which is a package that you can access from the SAS support website. The first step is going to be connecting to a CAS server. And this is the machine that is going to be running your analytics. That's where we are going to be training our agent. And this notebook communicates to that machine via port 33789. Once that is done, you load the reinforcement learn action set. So this contains the methods, the reinforcement learning algorithms that we are going to use. And let's go straight to the syntax of how you train an agent. We are going to be calling the RL train DQN action within the reinforcement learn action set. And syntax is relatively simple. So you do not need to deal with the complexities of what are the state variables, what is the definition of the reward, because that's all defined in the environment. The agent gets that information from the environment. And this is going to be the lunar lander environment. And that is going to be running at a different machine where you communicate with the IP address and port that you specify in the URL parameter. So notice that unlike other methods, unlike other actions, you don't have a CAS table. You don't have a table equals parameter because you're not using a data set. The communication with the environment is all that the agent needs to train. And how do you start an environment? This is going to be in a different machine, and this is again identified by the URL parameter. And in that machine, that would be really simple. You would use yet another SaaS package that you will be able to access, import a Gym compatible server, and simply start a server at a port that you specify. So it's really simple to start an environment in a separate machine, which then communicates with your agent. And we identify which particular environment we want from that Gym server by specifying the name. In this case, Lunar Lander version 2. And note how we also specify render equals true, which allows the environment and the agent to exchange enough information that you can have a graphical representation of how your agent is learning and how your environment is reacting. So in addition, you have a number of optimization-specific options. We are going to use the Adam algorithm for our optimizer. And after running, this runs for a few minutes, so I have pre-ran this code. You obtain some general information about the model that you've optimized and a few iterations of the optimization history, so where you see the reward going steadily up and what is the average Q value for the result, as well as average target value and test reward. Very importantly, you save your agent, your policy, under the name DQN weights, which then allow you to run this policy afterwards, which is very similar to the same process as you would score a predictive model. And we provide to you an action, RL score, which allows you to go back to the same environment now with a trained policy and continue to communicate. Besides the RL score action, we also provide RL export model action, which creates an A-store. So you could also do the same thing using an A-store and using the A-store.score action. And once you do score, all of these steps can take place in real time. And besides having output that describes for each action that you have taken, what was the state that was exchanged, what was the immediate reward, and whether or not that episode is done. And by the way, in the Lunar Lander, you are done when either you land successfully or you crash. But rather than go through this table of numbers, let me show you a graphical representation of what happens before and after training. So before training, let me show you an example of the behavior. As you can see, you start from the top of the screen. You are nowhere near landing between the yellow flags, and you crash all the time. This is what happens when your policy is not trained, and this is why you should use a simulator, by the way, when training your policy. Obviously, it would be a bad idea to try to learn on a real spacecraft. On the other hand, after you have trained the policy, this is what you observe. As you can see, both legs and smooth landing with velocity 0 when you reach between the two yellow flags. So you have essentially trained an agent that now knows how to learn a spacecraft on the moon, at least in this simulation. And this policy, by the way, all these actions are not predefined because, like in the real world, physics has variability. You never have the exact same sequence of actions and the reactions from the environment twice. You will really have learned to compensate for drift and other physical effects in this Lunar Lander example. So this was the demo. Let me go right back to the presentation. And I believe this is a fun little example, but besides games and toy examples, can you use reinforcement learning for real business problems? And the answer is definitely yes. And I will show you an example where we did a prototype, and in a very real sense, at SAS we eat our own cooking, and this is related to the cafeteria. And we have used internally reinforcement learning to try to optimize how many cashiers to have available during peak hours in our cafe. So that is based on cameras that are installed and that allow you to see, to count how many people are present, how many people are queuing up. So this is one such example of how you can use reinforcement learning to solve a business problem of how many cashiers to have in a retail setting. And you might, what is your state here? Well, you can use computer vision to identify and count people and estimate how long is the queue, how long customers are waiting on average. And the action is going to be, should I have 1, 2, or more cashiers in place at this particular 5-minute interval? So, and we have trained an agent, and while this may seem like a relatively simple problem, it gives quantitative, measurable benefits that you can compare against different types of algorithms used to solve this problem. You could use queuing theory to determine what would be a fixed schedule for having 1 or 2 cashiers during a certain period in the day. And we have compared what is the reward, and the reward is defined based on business key performance indicators that are of importance to this specific business problem. You get better, lower cost of operational cost by using reinforcement learning than any fixed schedule based on the classical queuing theory, and even than using a supervised learning approach where you would try to optimize each instant reward. Remember, long-term reward is the domain of reinforcement learning. Besides just retail applications, not just cafeterias, but these photos might seem a little crowded because they were taken pre-COVID. So besides retail, you might also want to solve similar problems in logistics, in warehouses, in traffic control, in vegetation management for power lines, and many other applications related with manufacturing, transportation, predictive maintenance. And by the way, reinforcement learning is a great combination with IoT because of the real-time and sensor-based nature of IoT. So in conclusion, reinforcement learning is a very promising field in AI whose usage is really growing up. It is available in SAS Viya, and we have an action set specifically for reinforcement learning, where we have added deep queue networks. We have added the ability to have custom environments as well as compatibility with standards such as OpenAI Gym, and we have emphasized usability and flexibility, where you have a well-defined and relatively simple syntax that you can use. I hope you've enjoyed this presentation, and thank you very much for your attention.